All right, this number e is called the natural base. And that seems really strange because why e? Why? Why would that be called the natural base? And it really has to do with the fact that the derivatives calculus in general is much easier if you use a natural base for exponential functions. So that's what we're going to do. We're going to do calculus with with exponential functions written in the natural base, okay, which is e. All right, and we can actually convert any exponential function to the natural base if we can rewrite b as e to the k. All right. Now to find the k value requires logarithms. So we'll do more of that in 109. But for now, it's good to know that we can also go the other way. If we have an exponential function written in terms of e, we can go the other way and we can rewrite e to the k. That is b, right? That's our growth factor. So, the behavior of an exponential function when it's written in terms of e is really similar to what we saw with the, we had q equals a b to the t, right? So the behavior is simple, it's similar, but it's just that b is equal to e to the k. All right, so a is still the initial value. It's the value when t equals 0. It's the initial value. E to the k is b. That's our growth factor. R, the growth rate, is just b minus 1, right? So we can, if we know b, then we can find the growth rate for an exponential function. And k is called the continuous growth rate. Okay, it's the continuous growth rate. All right, when k is greater than 0, we have exponential growth. And when k is less than 0, we have exponential decay, right? Because essentially if k is negative, then it's just basically 1 over e to the k. So it's a number that's less than 1, right? It's less than 0, and it's greater than 0. So e to the negative k would be like that. All right, so let's take a look at this next example. We have a population that's increasing from 7.3 million at a continuous growth rate of 2.2% per year. So that's the continuous growth rate. You have to read very carefully here because here they're giving you continuous growth rate. If it says the word continuous, then this is k. K is, now we want to express it as a decimal, so 0.022. All right. So if it says continuous, if it just says growth rate, then it's R. But if it's continuous growth rate, then it's K. All right. So that's the continuous growth rate. And we want to write a formula for the population, and we also want to tell what the units are of the dependent and independent variable. All right. So we're going to call this. I'm going to call it P for population. I know we used P for principal before, but I'm going to use p for population since it's a function. We'll say that p is a function of t, so I could write it this way. P is a function of t, and it's just, I'm going to put it in the form that I have up here, right? Because I'm given the continuous growth rate, then I can, that's my k value. The a value is the initial value, so the population is initially 7.3 million. So my p, the way I'm going to write this is my p will be in millions if I just use 7.3. If I write out 7 million with all the zeros, then my p would be in the number of whatever it is we're counting in this population, people or whatever it is. All right, so I'm just going to use 7.3. So my population is going to be in millions, and then e to the kt. So 0.022 t. That's it. That's the formula for this population growth because we were given the continuous growth rate, right? So P, the population, is going to be, is in millions. It's good to make a note of that so that if you use it, then you know what your answer represents. All right, so P, the population is going to be in millions, and T, because this is this continuous growth rate is given per year, right, then my t has to be in years. Okay, so it has to match whatever the, whether if you're given a continuous growth rate, it will tell you if it's per year or per week or per month or per day or whatever. All right, so those are the units of the independent variable t and the dependent variable p. P is in millions. All right, what is the rate of change of this population over the first year? All right, now be careful. We got lots of rates going on here. This is rate of change, right? This is the rate of change. This is essentially average rate of change. All right, so we need to look at what was the change over that first year. Now, p at 0, right, is just going to be 7.3 million. All right, so 7.3 because p is in millions. Now, I need to calculate what is p at 1. All right, if I put, I'm just going to put it into the formula that I have in part A. So e to the 0.022 times 1. All right, I put that into my calculator and I got 7.46 million. So remember, if it's just rate of change, that's the same as average rate of change in this case. So we're just looking at the average rate of change over the first year. So that's our interval. This is our interval that we're looking at. All right, so I'm going to take the so it's going to be, let me write this. It's going to be essentially delta P over delta T. Right, this is our average rate of change. All right, and so I'm going to take 7.46 minus 7.3 over 1 minus 0. Right, it's just a change in the population over the change in time. And so I got 0.162. So let's put some units on that, though. What does that mean? What does that mean? That means that the population is increasing by 0.162. So that, million people per year, if it's in people. I don't know if this is a rabbit population or or what. But essentially it's millions per year, right? Millions of whatever it is. So if it's people, then this would represent, be saying that the population is increasing by 0.162 million, which is really 162,000 people per year. Now, this is a nonlinear function, so it's not going to continue to increase at that same rate, but over that first year, that's the rate of increase for that first year. All right, so let me scroll down just a hair more. This last question asks, by what percent does the population increase each year? Okay, that percent increase, right? This is a percent increase, so this is our relative rate of change. This is our R value, right? So if we can find B, which is going to be e to the 0.022, right? I can isolate this. This is B. And so I can calculate the growth factor. It will be 1.0222. And so then R is equal to B minus 1. Right, so it's 0.0222, or we could write 2.22% per year, right? Because our time is in years. All right, that's our percent increase in 1 year. All right, that's just our growth rate. Okay. All right, well, that's all I've got for you, and I'll see you in class.